I'm going to mute the phone here. Okay. Say something so I can hear you. Paul, say something so I can hear you. Only hear the music.
Hey there, everybody. Dr. Daniel Barth here with episode 43 of the How Do You Know program. Scott Roberts is traveling and may be joining us from remote today.
I am.
There's Scott. Hey there, Scott.
How are you?
Doing well, thank you. And I am in the lovely high-tech Explore Scientific Studios up in Springdale today at the Explore store. So that's kind of fun. I got to come up and do a Amazon Live program with my good pal Kent Martz, and I'm hoping some of you all tune into that. It's a fun show about Explore Scientific products and science education and helping set hearts afire for science and mathematics with, well, kids of all ages, really. So as we get into episode 43, this is the... This is the crazy busy time of the year for me as a working professor of STEM education. We are entering the last 2 weeks of the semester at my university, at the University of Arkansas, and that means all the end of semester projects are coming in. And last week somebody said, well, how much stuff are you talking about when you're talking about grading, Doc? And so I went and photographed my 14-inch stack of materials, and somebody says, well, how much is that really? So I threw it on the bathroom scale, 17.4 pounds of paper to read through and grade. And that was just last week. I've got another stack coming in this week. But then thankfully the semester will be wrapping up the second week of May here. And I will have more time to focus on fun things like astronomy and science education activities that are outside the classroom. So we're going to have some opening comments today. We try to do this every week. We don't always get to it. But part of my prep for this show, friends, is I spent a fair amount of time I have a lot of news feeds that come in from NASA, from ESA, from JAXA, and different space agencies, and I'm looking at what they're doing. One of the fun things I saw, and how long have I been a space science fan? For more than half a century, since the Apollo era. And I just learned, I was today years old when I learned that there is a website that will show you what the Hubble Space Telescope is looking at live. And we have our show notes for today, which Scott is always kind enough to download, make available as a download for you. And there's a website called spacetelescopelive.org/latest. And when you log on to this website, it shows you what the Hubble telescope is seeing right now, which is, to me, so exciting. Hubble has been up there for more than 30 years, and we're looking at what's coming down from one of the world's first space telescopes right now. So it's a very dynamic and interesting thing, and you can see what Hubble is looking at in a little bit about it, which is a fun thing. And there's also a Space Telescope Live Twitter account. So if you all are Twitter users, that's another fun science adventure for you.
Right now, Hubble is acquiring a new target.
Yeah, every once in a while when you look up, Hubble will be slewing around to a new target, and so there will be no feed at that point. But it's fun. I've just become addicted to popping in and out. What's Hubble looking at right now? And of course, time on the Hubble telescope is extraordinarily precious. The process for getting in to get Hubble Space Telescope time, that's no small deal, friends. You have to submit a proposal, defend it, committees critique it, and other space scientists decide, are you worthy? Because there's only one Hubble, and there's lots of people who want to use it. The other thing that I was just stunned, and every once in a while I come across science news, and I'm just amazed. Some of you may be fans of the Star Trek universe in the various programs, and I forget which program it was, but they had the holographic doctor. He had no name. He was an emergency holographic program, and he would come online and said, what's your medical emergency? And the idea is if the regular doctor got sick or injured, that the holographic doctor could go ahead and tell you what to do. Well, guess what? We are living in the future, and NASA beamed a doctor up to the ISS as a three-dimensional hologram that people could see and view and interact with in real time. I am so stunned by this. And the Microsoft HoloVision camera system that they used for Xbox was part of this research, and they have a projector on the ISS, and they were actually able to beam a doctor as a hologram live into the ISS, which makes me think the next rover that goes up, heck yeah, I mean, how much would you pay, Scott, to be holographically beamed to Mars and to be able to look out and swivel around and see what you could see from the rover?
Probably a lot.
Probably
quite a bit. Yeah.
Oh yeah, and I don't think I could. Maybe Scott could afford it, y'all. I don't think I could, but maybe Explorer could afford to buy me 2 minutes on Mars. But oh my gosh, I realized that at my age, I am never flying to Mars. I dreamed of it as a kid. Oh my gosh, I went through. Oh yeah,
up there, right?
Yeah, to be able to go up as a holograph on the moon, on the ISS. I'm going to get 2 minutes on the ISS just to look out the window as a hologram, and somebody could take a picture of me as a hologram up there looking out the window. I would pay some serious coin for that. And you might say,
Yeah.
that's a frivolous use of technology in the international. No, it's not. Oh my gosh.
Not at all. In fact, it's a great use of
Not at all,
technology in the
because
internet.
when we make it real for people, part of what the astronauts in the Apollo program did for folks on Earth is they made space travel real to them. They were more than astronauts. They were more than scientists. They were fun, engaged fellas having fun doing science on the moon, and to some extent, we all went with them.
Sure.
That one of the last pictures of the moon, and I think it's Dave Scott, and he's jumping up and saluting, and his co-commander is taking the picture there, and just wow. Wow.
Live from the moon. I remember Apollo 11, they just had the headline down in the bottom.
Live from the moon.
Live from the moon. We're like, what?
Which we haven't done since 1972, Oh my gosh, it's
Right.
50 years since we've been to the moon with people, which is a
So can
shame.
you imagine what the video is going to be like? The video coming
Yeah.
back from the moon will be
Yeah.
crisp, clear, 4K,
Oh,
or
yes.
8K or whatever.
Oh my gosh, the people, I remember teaching high school and showing some of these Apollo videos to students, and they said, "Are you sure it's real? It's so blurry." I'm like, you guys know this is like 1960s TV technology. Yeah, it was quite low
bleeding
res.
edge at the time. Yes.
Yeah, yeah, absolutely. So, Scott, one of the other things we've talked about recently is we chatted about the solar tsunami. And we've
Yes.
had some, the sun is in a very active phase. We've had a lot of
Yes,
aurora. And people as south as the northern United States have been able to see some aurora in recent weeks. Well, we talked about this idea. Would the solar tsunami destroy our modern technological civilization? And it's interesting. The car website Hemmings, which is a car enthusiast website, Scott, they did some research and they looked up and they did some research on could your car survive an EMP? And they actually went to a facility and they took some relatively new cars from, I think they were surveying cars from about 2000 to 2010, some as old as 1990. And they were trying to decide would older cars do a better job surviving one of these solar catastrophes. And it was interesting. What they found is something I realized I kind of slapped my forehead. I should have known that. What they found was that most cars do just fine surviving a solar catastrophe. Because when we have this geomagnetic storm, what's happening is the magnetic field is waving. And it induces current. And we've all heard about the Carrington event, 1859. And this huge solar storm, auroras all the way down to Cuba. And they were saying that, oh, telegraph wires, they were having enough electricity to run the telegraph without batteries. The sparking caused some telegraph stations to start on fire. And they said, oh, well, this thing could be terrible. And in 1989, I believe it was, they had a very large solar storm that blacked out a large section of Canada. And what happened again? This waving magnetic field induces a current in a wire. However, it's not just the strength and fluctuation of this magnetic field that does this, Scott. What we've really got here, friends, it's also the length of the wire. If you were ever the kind of kid who took things apart, I did.
Yeah.
And you ever, Scott, did you ever take apart an electric motor?
I took apart everything.
Oh, okay. So
the toy that I got for Christmas, it was apart. You know,
Exactly.
I had to see the motor, I had to see how it worked.
my mother, God bless her, used to tell the story that as a 6-year-old, I took apart her very expensive Electrolux vacuum cleaner. And she called my uncle, oh my God, Danny's taking apart my vacuum cleaner. And you have to come over here. By the time my uncle got over, I was afraid I was going to get in trouble. I reassembled it. And my mother said, don't touch it. And he said, well, and so he used his foot and turned it on, and it worked. Well, if you were a kid and you took apart an electric motor, what you may have found was that in the interior of the motor, what we call the armature, it's layers and layers and layers of wire. And what we don't realize is it's one long string of wire, many, 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 many meters of wire to make a little tiny electric motor. It is this length of wire that makes it possible for the magnetic field inside the motor and the alternating current to generate rotary motion. When we're talking about telegraph systems in 1869, we're talking about hundreds, thousands of miles of wire. When we're talking about the Canadian blackout, we're talking about generating systems which were not prevented from getting overloads. If you've got a surge suppressor on your computer at home, friends, as you're watching us, you've got technology that would stop an electromagnetic pulse or a geomagnetic storm from damaging your equipment. If you unplug your computer system, because we have warnings for geomagnetic storms. We get warnings of up to a couple of days. If you've got your computers and your televisions and your sensitive electronics unplugged, chances are they're not going to have a problem. When Hemmings tested cars, and they did, the United States government did a test called Starfish in the 1950s. They deliberately exploded a nuclear bomb in the upper atmosphere to create an EMP, and it blacked out radio transmissions across Hawaii for days, for a couple of days. And this was about, I believe it was 5 kilovolts per meter. They tested cars up to 30 kilovolts per meter, much higher than most geomagnetic storms. And they found that most cars had no effect at all. The wiring is so short in a car that it didn't really burn anything out. Now, some cars, about 20...
Let me ask you a question, Daniel. This
Sure.
This is before cars had computers in them, okay? So
They were cars
what
with
about today's
computers in
cars?
them, and some of them with dashboard electronics like GPS and navigation systems.
Okay.
And they found that sometimes some of the cars had malfunctions in the dashboard electronics, but
Okay.
in all but I
That's
think
right.
one case, when they shut the car off and restarted it, it rebooted the electronics and there was very little in the way of lasting damage. No cars were shut down while running because they tried this test with the cars off and the cars on. With the cars off, they didn't find any damage in any of them. With the cars on, some of the cars had glitches like lights would blink or a check engine light would come on. The GPS wouldn't work, but they turned the car off and on again. In all but one case from all the cars they tested, they had no permanent damage. They had some nuisance damage where they might have to replace, a relay or something else like that. But in no case did they have a system where the car was stopped. You see this like movies like The Day After, where all the cars come to a grinding halt on the freeway because the nuclear blast has gone off. Not happening, y'all. Not happening. The cars were not stopped dead in their tracks. None of them were stopped dead. And so this gives me hope that maybe civilization can survive the next tsunami. The other thing is that basically since the 1950s, the military has worked at hardening their electronics. And because of interference with ever more powerful LiDAR, radar, and wireless communications, most auto manufacturers harden the electronics in their cars just because we use so much. We have cell phones and everything, friends. We use so much more radio frequency energy now than we ever did 20 or 30 years ago that your car is probably going to survive the next solar storm, which is good news. The other fun thing in the news this week, Scott, it has to do with NASA and the InSight probe. The InSight probe is a lander that touched down, and they put probes in the soil to measure seismic activity. And the InSight probe measured the 2 largest quakes on Mars to date, 4.1 and 4.2 on the Richter scale.
Wow. You can feel those.
What's neat is, those of us, Scott and I, have spent a significant amount of time in California. You can feel a 4-point earthquake.
Yeah.
You know, you bounce for, and
it's not horrible, but you can feel it. Yeah.
one of these earthquakes went on for over 90 minutes. It just kept vibrating.
90 minutes. That might create some damage.
It's crazy. If you're a Californian or if you're in an earthquake-prone area, you know 30 seconds on Earth is a horribly long earthquake.
Yes. So 30 minutes.
Yeah.
That's going to damage buildings or underground facilities.
Underground
that we
structures,
have
yes.
or whatever. We're gonna have to reinforce those things when we get there. So okay, so you had a 30-minute long earthquake. What's
Yeah,
the
more than.
longest earthquake they would have, right? So
Yeah.
you don't know. Is it
And,
an hour? Is it 2 hours? All day?
I don't know. I was stunned by this. I experienced 3 earthquakes over 7.0. The Hector Mines earthquake, the Whittier earthquake, and the Upland quake. I was right within 2 miles of the epicenter of Upland, which was horrible. Not a recommended ride for the theme park friends.
Right.
And 4.0, 4.1, 4.2, you can feel these. You can feel these.
Sure.
And I don't know how long earthquake detectors could detect the vibration on Earth. I really do not know. And but these quakes went on for quite a long time on Mars. These were located in the Valles Marineris, the large Mariners Valley on Mars, which is a big graben. Death Valley on Earth, friends, is a graben. It's a place where the crust spreads and sinks. And this giant tectonic fault on Mars, we always suspected it would be the source of seismic activity, but we had not detected substantive quake activity on Mars before this. So little earthquakes, but the nice thing is big quakes like this, they act as a seismic probe and they let us see the interior structure on Mars. So look forward in the next coming months and years, data from these quakes being analyzed to tell us more about the interior structure of Mars and what is seismic, and is it still molten in the interior? Are there movements in the mantle? Many of these questions should be answered by these bigger quakes. So that's very exciting. Anyway.
We have some comments here, and
sure.
I should probably give a shout out to the people that are watching today. We have we've got Chris Larson who says hello. Mike Wiesner's on. Says howdy, students of Dr. Barth. Dad Frequency is watching. Martin Eastburn is there. Howdy from stormy East Texas. Harold Locke is there. Let's see. Mike Overacker. Of course, myself and Dr. Barth. And I was, and Dustin Gibson gave a little quick shout out for us. Thank you. And let's see. If we can, it would be nice to put in that link for the Hubble Space Telescope Live.
Okay.
So that would be nice. What else? Martin Eastburn says, Hollow is right. Read today, a moon of Mars is crashing into Mars. Okay.
All right.
And Jim's Astro says, my truck didn't survive the Michigan winters. I wonder if it was because of electromagnetic or because of all the salt and the cold and, you know, I mean, it's brutal up in Michigan. Harold Moss says to induce current, the magnetic field has to pass perpendicular to the wire. Okay.
Yes, the wires have to, well, perpendicular is kind of an odd thing. The wires have to move through the electromagnetic flux. And I'm not going to get into a lot of EM theory here with our friends, but yeah. Basically, you can do it 2 ways. You can have a motor where the wires move through the magnetic field, or you can have a magnetic field moving across the wires. Many of us have done this experiment, Scott, where we were in school and we had a coil of wire hooked up to a volt or an ammeter, and we move a magnet through the coil, or you move the coil across the magnet, and either way produces fluctuations in current, which you can measure and see. It was a very simple high school experiment. Goes back to Professor Faraday in the 1860s, somewhere in there. Earlier than that, 1830s maybe. So, yeah.
I remember making a crystal radio, a crystal
Yes.
AM radio. I was able
Yes.
to pick up stations with, and I remember winding wire around
Yes, I
something.
remember
So
going out and stringing wire on up on the roof, putting up nails in the roof and
You're
stringing
getting
wire
serious.
across. Yes,
Yeah, I just had
absolutely.
the little thing, but I remember hearing the radio, and I was like, "How the hell does that work?" So it was
Yes,
cool.
it was
cool.
quite stunning.
Yeah.
So,
Mark
and
Eastern's talking about the earthquake series. Says that would move a rock along the path in the wave it generated. Wow, wonder if ours wonder if ours in Death Valley. Okay.
it would be
and Harold
fascinating
says,
to be an astronaut on Mars and experience a quake.
sure.
And
Absolutely.
for those that were interested, I'll give that link again. It's real simple for the Hubble. It is Space Telescope Live, all one word, spacetelescopelive.org/latest. So there you go, spacetelescopelive.org/latest. And that's that link to see what's happening with the Hubble Space Telescope right now. It would be very cool if they would have a, perseveranceroverlive.org, but since there's a 20-minute transmission delay, I don't know if we'll ever get that. But that NASA, if y'all are listening, that's my suggestion box suggestion for the week. So let's go ahead and jump in today's topic, the earliest life on Earth. Earlier today, I was helping out on an Amazon Live program here from the Explore Studios, and we were looking at a small geology microscope, a stereo microscope, very nice instrument. And you could, with such an instrument, you can look at rocks, and if you have access to them, you could look at a fossil and see structure. Well, what's interesting, people are always trying to find what's the oldest fossil. The question, when did life on Earth begin, and did it leave any fossil evidence for us? Now, when you realize we're talking current theory has been about 3.5 billion years ago was the earliest life. That is the currently accepted, widely accepted theory. And some of the fossil evidence are stromatolites, which are basically big mats of algae and bacteria. We figure some of this earliest cellular life was just huge mats of single and multicell bacterial colonies and algal colonies. And we believe that much of this early life was not much like life on Earth today. It would have been anaerobic, meaning it could not tolerate oxygen in the atmosphere. The atmosphere, according to Harold Urey and Miller and all those folks, it would have been a reducing atmosphere, methane, ammonia, not an oxidizing atmosphere. And so the atmosphere itself would have been toxic to 99% of life on Earth today. And these mats didn't live on sunlight. People think, oh yeah, plants. No, no, no. The earliest life on Earth, Scott, would not have been photosynthetic. Photosynthesis was an adaptation of life which came hundreds of millions of years later. The anaerobic bacteria came first and the anaerobic algae. And these anaerobic bacteria, they were basically chemicophagus. In other words, they ate direct chemical energy. They survived on things like metal ions and sulfur and phosphorus. This is the kind of life that we find today at the bottom of the seafloor at some of these hydrothermal vents. If you go to your search engine, there you go, you go to your search engine and you put in black smoker. And what you'll get an image of, folks, is a hydrothermal vent at the bottom of the sea where gases, sulfur dioxide, gases made from sulfur and phosphorus that are almost black, are erupting out of the seafloor, and it looks like smoke coming out of a small volcanic vent. And you're getting water with all these dissolved minerals, phosphorus, sulfur, iron, and the life forms there don't use any oxygen because 2 or 3 miles beneath the sea, there's no photosynthesis because there's no light. And secondly, there's no metabolism as we normally think of it because there's no oxygen. These environments are practically oxygen-free, and these volcanic vents on the bottom of the sea are putting out very hot gases, and what you see is kind of weird. The life exists in this ring around the vent. Too close, and you literally are cooked to death. Too far away, and one, you freeze to death because the water is very cold, and number two, you have no food source because these primitive forms of life, and they may be ancestors from some of the most primitive forms of life. We find the same thing deep within the Earth's crust. Many kilometers down, there are bacteria that are native to that environment. They are born, die, and have lived for billions of years, many kilometers below the Earth's surface. Obviously, no oxygen there either. And we say, okay, well, can we find a fossil? And when you find rocks, then the argument comes up, gee, is it really a fossil of a living thing, or is this just geology? When we had we've talked about the Allen Hills meteorite before, Scott. This is that meteorite that came from Mars. We've proven from gases and isotope ratios inside the meteorite that it has Martian origin. There was a huge asteroid impact. This chunk was blasted into space, and it orbited in space for some millions of years, and then it hit and landed in Antarctica, I don't know, 13 to 15,000 years ago, and it sat in the Allen Hills region, which is an Antarctic desert. They get a couple of centimeters of snow a century. It's one of the driest, coldest, most Mars-like environments. The rock must have felt right at home. Because it's a dry, cold, high radiation, ozone hole, lots of UV, it's the most Mars-like environment on Earth. The rock sat there until it was collected, and then it sat in storage for a few years, and somebody finally went in, and then they went, wait a minute, microfossils. And of course, the announcement in 1992, President Clinton made the announcement, we found fossil evidence of ancient life from a rock that came from Mars. And the controversy and the conspiracy theory machine, and the controversy has not died out to this day.
No.
And I think the only thing that's going to silence this is if we go to Mars and we do find either living microenvironments or we find fossil evidence of ancient microbiota. But right now, these new researchers, they had some rocks that they took from a place called Jack Hills in Australia. So out in the outback in Australia, there's these rocks that are the oldest rocks still on the surface of the Earth. Now, the Earth is not a static environment, and over tens and hundreds of millions of years, we know that the crust is recycled. We have places like the Mid-Atlantic Ridge, where volcanic material is coming up 24/7, 365, producing new basaltic crust, and this crust pushes and spreads the American continents from the European and African continents. And then there's areas in the Pacific, the Ring of Fire, where we have subduction zones, where crust is expanding in one place, in the other place, that crust is diving, one plate dives beneath another, and these subduction zones are where we have the very worst earthquakes. the Fukushima earthquakes, the huge 8 and 9 earthquakes along the coast of Alaska, Chile, these tremendous earthquakes in the Indian Ocean that produce these huge tsunamis. These are from the subduction zones, where suddenly the Earth slips and this crust dives beneath. The Earth actually shrinks by some meters and the rotation rate changes, just like a skater pulling in their arms and spinning faster. So the Jack Hills rocks, 4.4 billion years old. They're looking at fossils that they believe, and you're not doing carbon dating in this stuff, folks. Just to let you know, carbon dating will take you back about 50,000 years. So if you discover an ancient pit where ancient peoples tossed away their bones after dinner and their refuse, or a burial mound, and if it's within the last 50 or so thousand years, radiocarbon dating. If you found a Neanderthal site that is 2 million years old, sorry, radiocarbon dating isn't going. If radiocarbon dating registers, it's a fake, right? You find in Neanderthal bones that radiocarbon date, no, sorry. Neanderthals were extinct, and we do these isotope measurements, and we can radiologically date using uranium, phosphorus, other compounds, and these very, very long-lived compounds, and we can date these things confidently to about 4.4 billion years old. The Earth itself is 4.5 billion years old. So the Earth would have taken 500 million years or so to coalesce in an accretion process. Many, many bombardments, and we've talked about the accretion process before. Dust grains stick together, you get to something between 100 and 1,000 kilometers, and it starts to compress itself. You start to change things geologically at the core. It gets big enough, gravity begins to be a player, and it's not just random collisions anymore, it's actually drawing things in. Well, the interesting question is, well, if the Earth is accreting from impacts and things sticking and hitting and colliding, how long did it take for a modern Earth where you've got a crust, a mantle, and a core to form? A lot of people have this mistaken idea that what you have is you have this very lovely Earth forming very early, where there is this mantle of iron, and then there's this layer of liquid rock, the core of iron, the mantle of liquid rock above, and then you're talking about, oh, there's this crust on top. You realize the heaviest granite and rocks that we have on the crust of the Earth, Scott, are the things that float on the denser rock of the mantle? Isn't that crazy to think about? The basaltic crust is the lightweight stuff that floats on this much denser liquid mantle. Well, the interesting thing is the modern planets form from the inside out. What really drives this melting process inside is two things. Heat from gravitational pressure. Pressure creates heat. We know this is true. But the other major force that drives this melting of the interior forward is radioactivity. And we think, oh, doesn't radioactivity penetrate things? Yes, but when you're talking about rocks hundreds or thousands of miles below the surface of the Earth, that radioactivity is all absorbed eventually by the rock around. And all that radioactive energy turns into heat. That heat melts the rock and makes the core molten, and it makes the mantle molten. But more importantly, if you think about it, Scott, at one point, the Earth was just an undifferentiated jumble. Think about a container of Rocky Road ice cream you just brought home from the store. Yeah, sure, there's marshmallows in there, and there's almonds in there, and there's pieces of chocolate, and there's the regular ice cream. But put your block of Rocky Road ice cream in a bowl and let it sit on the table. As it melts, it will differentiate itself. The walnuts will sink to the bottom. The chocolate, being dense but less dense than the nuts, will form a layer on top. Then you'll have the liquid ice cream, and floating on top of that will be the marshmallow pieces. This process of differentiation occurs inside planets as they melt themselves from the inside out. The Earth took some hundreds of millions of years to get hot enough to become molten. The iron sunk to the core. The iron and nickel were the densest materials. They formed the core, and then the still heavily dense but lighter rock of the mantle formed the liquid mantle around the core, and the marshmallows on top are things like the granitic and basaltic crust that we see when we climb a mountain and we see exposed rock on the surface of the earth. That's the marshmallows floating on top. Well, we think this took somewhere between 100 million years. The oldest continents, you think, gee, how old are the oldest continents? Well, the oldest continents are about 4.5 or 4.4 billion years. It took about 100 million years for these continental crusts to form. Life begins almost immediately. The fossils these Canadian friends are looking at, 3.75 to 4.2 billion years old. If they're 4.2 billion years old, that means they're at least 300 million years older than the oldest life we know of currently. We're pushing back the date of the origin of life, and we're also saying that, if the continents took 100 million years to form, literally by the time the continents are forming and becoming solid, life is forming and colonizing the surface of the earth. To me, this is stunning. This is absolutely stunning. Well, we'd have to go look that up.
It almost choked you to death.
Anyway, let's go ahead back to our fossils. Part of the question here, friends, and the crux of the argument, how do they know they're really fossils and not geological processes? This is the exact argument that's been going on for 30 years with the Allen Hills meteorite. How do we know these are biological fossils and not just forms from geology? Well, one of the things that they're seeing in these, we're just going to call them fossils for the sake of argument today, friends. One of the things we're seeing in these fossils is we're seeing tubes and filaments. And again, these are nanometer size, much smaller than current bacteria on Earth, and they're being cited as being of biological origin. Now, this is disputed by other scientists, and the authors, the people who studied this and are making this claim, they're saying there was a diverse microbial ecosystem on Earth 4.2 billion years ago. And their basic argument, if you can have this diverse microbial ecosystem forming on the Earth just 100 million years or so after the continents become solid, and it may have been contiguous with the continents becoming solid, if life forms that quickly and that easily, they said this may be a common phenomena on other planets and moons.
Yes, yeah.
If life self-assembles here in the geological eye blink after the continents become solid with a nasty poisonous reducing atmosphere, methane, ammonia, nitrogen gas, nothing like the friendly Earth we know now, why couldn't there not be microbial systems elsewhere? Interestingly, We think it was metals in the crust that formed some of the first food sources for this early life. We've mentioned, Scott, the sun was not a food source here.
Right.
Photosynthesis came along much, much later. So we're talking pure mats of bacteria, anaerobic bacteria. Basically, in all life, we're really talking about electron transport. It's the ability to manage the energy from the transportation of electrons that allows life to have energy for biological processes like reproduction and metabolism. Well, one of the easiest ways to transport electrons is using metals. Today, hemoglobin uses iron, and chlorophyll uses magnesium, and we see other organisms with blood and biological materials based on copper and other metals. You see this all over the place. It's really believed that everywhere we have iron ore deposits today, ferric oxide, what we have is large, shallow seas which were full of ionized iron. The bacteria consumed this iron and deposited iron oxide and made iron ore deposits on Earth are basically bacterial colonies. They're the remnants of bacterial colonies. This is not the same as a fossil record, but people have argued, Zubrin and many others have argued, that the biggest evidence for ancient life on Mars is that it is indeed a red planet. Mars is covered with iron oxide. This is what makes the soil red, orange in color around that planet, virtually everywhere. Now, some of that stuff would have been wind transported, but it argues for a large community of bacteria that were consuming ionized iron in shallow seas and depositing it as ferric oxide, hematite, and other things.
And maybe now deep inside of Mars, the process is still going on.
That's an excellent question. That's an excellent question. We know Mars has reservoirs of water underneath. We have seen evidence for brief outflows of liquid water on the surface. There certainly is sufficient pressure underneath and tectonic activity now that there could be pockets of liquid water, just as there is under the glaciers in Antarctica. And it's the process of heat from tectonic events that keeps that water liquid.
Yeah.
You certainly could have these processes underneath the Martian crust.
But we still have earthquakes there.
We still have Marsquakes, right? We have an active tectonic system. And it is these metal binding proteins, what we call ferrophagic life. Iron ions converted to ferric oxides and metal deposits. Metal binding proteins might have been prebiotic. In other words, metal binding proteins might be some of these things that self-assemble as amino acids do. And we look at this. The other thing we're looking at, Scott, and the other thing that these authors cite, they're looking at an imbalance between carbon-12 and carbon-13. Now, or excuse me, carbon-14. Carbon-12 is favored by biological life. When we see carbon in geological processes, carbon being fixed in carbonate rocks in the soil, for instance, well, we don't see any preference for carbon-12 or carbon-14. The ratios in the atmosphere are the ratios in the rocks. However, when we look at fossils, when we look at biological processes, biology tends to heavily favor carbon-12, and no one really knows why. The chemistry of carbon-12 and carbon-14 are, as far as we can tell, identical. Only the nuclear properties are different. Carbon-14, C14, is radioactive. Carbon-12 is not, at least not on any significant level. And so why does life favor carbon-12? We don't know. But we know that all earthly biological systems, when we fix carbon in biological processes, whether we're talking about photosynthesis or tissue building in mammals, insects, fish, doesn't matter, we tend to favor carbon-14. And when we look at a fossil, one of the ways we know it's a fossil is that there's an anomalous ratio of carbon-12 to carbon-14. We call it carbon-12 enrichment. These fossils in Canada show carbon-12 enrichment. One of the interesting things is there's many geological samples from Mars today which show carbon-12 enrichment. Now, there are people who just pound the table and say, no life on Mars, and that's been going on for a century.
Yeah.
That's been going on since Percival Lowell's time.
Right.
And they say, oh, well, there's various theories. Geochemistry on Mars may be different. That's really unlikely. The chemistry of life might be different, I'll grant you. The chemistry of rocks and water and acids and bases, I find that harder to believe. There's no known geological process, none, that concentrates and enriches C12, except biology. People have proposed, well, perhaps Mars flew through a cloud that was rich in carbon-12, and it was preferentially incorporated into geological rock processes several billion years ago. I find that groping for straws. As Aristotle would say, an improbable possible. Now, has anyone come up with anything from a rover that looks like a fossil? We have not. Do we have agreement in the scientific community that the Allen Hills meteorite contains microfossils? We do not. And so this is one of those cutting edge situations in science. And I have people when I talk about this and they go, but Doc, which one is true? What's the answer? And they're very unsatisfied when I say, I don't know, neither does anybody else, but we may have to wait decades to find out. In my case, I don't know how many more decades I got to go. So y'all get on it. I would love to have an answer. NASA, ESA, JAXA, y'all listening? Let's go. Next rover. I would love to know the answer to this. I know what I believe, what I intellectually think is probably true, but that's not science, Scott. That's futurism. That's speculation, and I'm honest enough to actually go ahead and admit that up front. Do I believe there was ancient life on Mars? I do. Do I believe that the Viking probes detected microbial life? I do. Can I prove that? I cannot. It's going to take more data. It's likely going to take boots on the ground. If they are interested in having an old bald guy on their team, I would happily take a seat on that rocket. My wife was like, you would not. I'm like, yes, I would. Sorry, honey. I would climb on that rocket. If they said, Doc, it's a one-way ticket. It's like the rover. You can go, but you're not coming back. Sign me up. I'm ready to go. And I think really, Scott, there would, if you said you can go and spend the rest of your life exploring Mars, but there's no return ticket, I think there would be no shortage of brave men and women from America, from countries around the world, who would have the skill set, have the desire, and they would say, this isn't suicide, it's exploration.
It's exploration. That's right.
It's exploration. How many people throughout history have advanced science by literally being willing to give their life so that others to peel back?
That is what humans have always done.
It's what we've always done. It's what we've always done. That's right. It's what we've always done. And it's quite spectacular, and I would be willing to go. I suspect I would not be anywhere near the top 1,000. They would have people younger, fitter, more qualified than me and you, but they would. I saw this thing, oh, we don't want to send people to Mars because they would have a 2% increase in the chance of cancer during their lifetime. Hello, the Apollo, Buzz and Neil were told, you know what, it's a coin flip. 50-50 we get you back here.
50-50.
Nobody's ever done this before.
That's right.
And they said, we don't care, we're ready to go.
We're ready to go.
Strap my butt to a rocket and light this candle. Wasn't that the famous quote from Alan Shepard? Let's light this candle.
That.
I think it was Alan Shepard. In any case, it was one of the early astronauts. They were all willing to die.
Yeah, they all watched rockets explode on the pad. They knew what the
Sure.
was.
Well, we talk about the Challenger. The only crew member of the Challenger who bought life insurance was Krista McAuliffe, the teacher. All the professional astronauts said, no, it's, risking my life is part of my job. It's what we do.
Sure.
So when the rocket is ready, whether it's NASA, whether it's ESA, whether it's Elon Musk and SpaceX, folks, I will pay my $1,000 for my lottery ticket to go, and I will not be like the guy who had the seat on Blue Origin and backed out at the last minute. Strap me in, I want to go.
So I'm asking the audience, how many people go on a one-way mission to Mars?
I would be willing to bet most of them. And we are talking about a group of space enthusiasts, it's true. But I would bet most of them would be, hot dog, let's go.
It says, just like the scientists, Harold Martin Eastberg saying, just like the scientists that go and clean up nuclear disasters and more volunteer. That's true.
It's true. It's true. Wants to go cave spelunking on Mars? I would love to do spelunking on Mars.
Right?
The idea of spelunking on Earth scares me to death, but I'd be happy to do it on Mars.
Right.
My goodness, to be able to find a microenvironment in a cave, you break through a wall and you realize it's a microenvironment. How exciting would that be?
Right.
Howard Carter, what's in there? Things, wonderful things.
Sure.
Sure. Frank Bowman, the character in 2001, played by Keir Dalia. Oh my God, it's full of stars. Yes. When I see these, it's too risky. I'm like, you insurance agents need to get the hell out of the space business and make room for the real heroes, the brave men and women who basically say, my life is a small price for being one of the first ones to explore this fantastic new frontier.
Yep. Well, Daniel, thank you for today's program.
They can be in my crew.
Yep.
Y'all are in my crew, guys.
And thanks for letting me tune in remotely here. This is cool.
It's a joy as always.
Yeah. I want to thank Paul Newton for producing all of this for us. And tomorrow we will not have a Global Star Party because I'm still out of town. So we will follow up next Tuesday with the 92nd Global Star Party. So I'll be updating you on that. And I will be back in town by Thursday. So you'll see me back on the air here, probably from my office. So, but thanks everyone. Thank you, Dr. Barth, and you guys keep looking up.
Thanks everybody. Bye-bye now. Bye-bye.